trouble with. Okay, so properties of exponents here. What are we going to do with this? And there are many different ways to do each of these problems. Let's see if we can maybe try to come up with the best, or at least, seemingly the best. I'm not going to say that you couldn't do this a different way and be just as successful with it.
You just review.
Probably. What do we think about this? Is it better? Is that better, or is that better? That's better? Okay.
Yeah.
So what are we going to do here? What's probably the first thing we want to deal with?
Negative.
Okay, I'm seeing this -2. So I'm taking this quantity in here to the -2. So what do I
Move it up.
say it again? Yeah, we could. That's true. We could move it up. Before we do that, though, how about if we? Because when I distribute this, look what's going to happen. When I distribute the -2, because that's what I'm going to do, isn't it? This is the property where if I have a times b to the m, that's equal to
A and B.
a to the m times b to the m. So if I've got a product and I'm taking a product to a power, I distribute over the product. In other words, to all parts of the product, right? And so that's going to give me then on the bottom, on the top, I still just get my 6 squared. On the bottom, I'm going to get 6 to the 4. Okay. Times to the -2. Okay. Now, and that's why maybe we don't want to move it to the top first. Maybe we want to wait and see where these bases are going to end up. Okay. Now, do I have any like bases?
Nope.
Yeah.
I do.
Oh, yeah.
6s. Okay, the 5 is a loner. That one's already by itself, but I've got there's a 6 and there's a 6, right? Okay, so I've got to deal with that now. What's my rule about? Okay, yeah, good. So we said if we divide like bases, we're going to subtract the exponents, but we're going to add something to that. We're going to keep the base where it has the most power to save some steps. So we're going to keep it where? Where does it end up? Bottom or top? Bottom. Because 4 is a bigger power than 2, right? So we know that the 6 is going to end up on the bottom. So if I write this out then as a fraction, I'm going to have the base 6 on the bottom to what power?
Second.
Yeah, to the 4 minus 2. Okay. And on the top, I'm going to get. Oh, actually, where does the 5 go? Is there anything on the top?
The 5 squared goes.
Okay, good. Because I've got a negative sign on the bottom, we said that in a fraction, a negative exponent is always positive in the other part of the fraction, right? So if it's negative on the bottom, it's positive on the top. And so my answer just ends up being 5 squared over 6 squared, which is what, 25 over 36? Okay, make sense?
Yippers.
Okay. All right. Now, something I want to show you, just to show you that this is consistent with another thing you might naturally do. If I'm doing the quotients of like bases, so dividing like bases, here's another way to look at this. What if I have like x to the 7th over x cubed? Okay, think what that really means. What that really means is, what is x to the 7th equal to? Yeah, I put that away. Say it again. X times x times 7 times, right? So I'm going to get a string of 1, 2, 3, 4, 5, 6, 7, divided by. Okay, so what am I really doing here? Yeah, I'm just canceling those, leaving me with to the 4. And so that's another way you can kind of visualize that a little bit. So really what I'm doing is I'm kind of just canceling them. If I'm going to cancel out 3 of those bases, that's going to leave me with 4 on the top, isn't it? So the bottom's going to go away completely. Does that make sense? I've crossed all those out. Cancel them all. Yeah. Okay. So there's one. Okay, another one I thought maybe we wanted a quick look at was this guy. There's a little trick here that's good to know about. Something like this. Okay, what should I probably do first? I think it's supposed to be, hang on, it's supposed to be a positive 2. Whoops. Not a negative 2. Not that it really makes that much difference, but. So if I'm taking, now at the outermost, if I kind of focus, if I start on the outside and work my way in, what property is going to apply first? I've got something, so I'm not even worried about that yet. I've got a power to a power, and so what do I do if I take a power to a power? Multiply the exponents. Good, so I'm going to get 2/5 to what power? -6. Good. Okay. Now, this is where I want to show you something. What happens if I take a fraction to a negative power? We said, remember, that if I have a negative exponent is always positive in the other part of the fraction. So if I were to distribute this -6 to both parts, isn't that just going to kick the 5 up to the top and the 2 down to the bottom? Okay, and so here's a general rule. Whenever I take a fraction to a negative power, what can I do that's kind of tricky? What would that equal to the +6? The reciprocal, exactly. Okay, so if I take a fraction to a negative power, it's always equal to its reciprocal to the positive power. Okay, so we could write that as 5/2 to the 6th, which is going to be 5 to the 6th. That's a really big number. I don't know what that is.
Oh, it's easy.
I don't want to think about it, but somebody. Well, actually, here, I'll calculate. Never mind. I'm gonna cheat. $15,625. Okay, so we get 15,625. 2 to the 6 is what? I think 64. Okay, so there's our answer. Okay. All right.
Told you that.
All right. Okay, here's another one. Thought it was kind of a good one to look at. Yep, these are just 6-1 type problems.
I'm not there yet. You're a liar.
No,
Yep.
would have gone there. What would we have entered, like,
Say it again.
like how would we have entered the 15,625 versus?
Yeah, no, you would have entered that final big fraction. Yep. No, okay, I'll tell you what. Good question. Good question. Let me go back for a second. How do we know that this couldn't be reduced? Because it can't be. It's a good question, but how would, it looks like a big ugly fraction. You might be thinking, oh man, do I have to try to reduce that? Look where it came from. 5 to the 6th over 2 to the 6th. Is 2 a factor of 5? Does it divide into 5? No, it doesn't. And this big number on the top is built only from 5s, right? It's 5 times 5 times, does that make sense?
Yep.
And so there's no way, if that's built only from a product of 5s, if I were to factor that into prime factors, it's just going to look like 5 times 5 times 5, etc., right? The bottom is going to look like 2 times 2 times 2, etc. So because 2 doesn't go into 5, 64 can't go into this big ugly number because this one is made only from 5s and that one's made only from 2s.
Can you divide it by like 2 or whatever?
No, I can't, because how could 2, hey Quentin, how could 2 divide evenly into a number on the top that's built only from 5 times 5 times, see what I'm saying? Make sense? Now if this had been like a 6 in it 2, well then we could have reduced it, then what we should have done is said 6 divided by 2 is 3, and then cube that. And if we didn't do that, we would have gotten big numbers that would have reduced. But because I can't simplify this fraction, I'm just going to get a big ugly fraction that I can't simplify either. Good question. Okay, so
The scientific notation, all this stuff would be on the test.
yes, not a lot at all.
Okay, I don't like that.
Didn't like you.
The test don't like it.
Right, okay. I like the sauce one. Yeah, that's the I like the sauce.
She's like, what? She's like, what? We're going.
Okay, what about this guy? Now let's take a look at this, please. Okay, we can make it looks ugly, but we can make this much, much simpler, right? When we multiply, when we're going to simplify this thing, we got 2 fractions. When we deal with fractions, we always just multiply straight across, right? Okay. What we could do here is we could, I'm going to show you this one way, and then you'll be able to take a shortcut in your mind after this. Let's break this thing up. There really are three different kinds of things going on here. We've got some numbers, and we've got two different kinds of bases, x's and y's, right? So let's split this up into the number part. So on the top, if I just multiply straight across, the numbers I get are negative 7 over 3 times 21, right? Times. Oh, we're going to. We're going to. But that's just the number part for now, right?
Okay.
Now, what about the x part? Well, it looks like I've got on the top, I've only got a single x to the 1, right?
Yes, sir.
So I've got x to the 1 divided by x to the 5th. I only get a couple of those. And then the y's. Oh, damn. Times. What about my y's? On the top, I've got a y to the 9th times a y to the 1.
Y to the 10.
And on the bottom, I've got,
Y to the negative 7.
okay, right?
Oh my god.
Okay, now, did I need to do that? Probably not. But just for now, at least, in our mind, we want to divide out just that we're going to break this up into parts. First, we're going to deal with the number part, okay? Now, what's the easiest way to do this? Be logical. Do I want to just multiply, or would I rather reduce first before I multiply?
Reduce.
Reduce. Can I reduce any of these things? Yeah, I can. 7 over 21, and these are being multiplied, so I can do this, right?
That was a point.
No, it's up here. Maybe let me do this. It's at times. So if I reduce this, I'm going to get negative 7 over 21 is going to reduce to negative 1 over 3, right? Okay, and so then in my answer, in my big answer, I'm just going to get a negative 1 on the top, and I'm just going to make that a negative sign for now. Okay, and here's my thinking. If I end up with some other stuff on the top, then I'm not going to write the negative 1 times something anyway, right? Because I don't write things like this. I wouldn't write negative 1 times x. I would just write that as negative x, for example, right?
Yeah.
If I end up with everything being on the bottom, then I'll turn that into a negative 1 to hold the numerator for me. But otherwise, we just want the negative sign there, okay? On the bottom, I get 3 times 3 is 9, right? We're done with the blue. Let's move on to the red. What about the x's? X to the 1 over x to the 5 is what? X to the 4th, where? On the bottom, right?
Yeah.
Because the bottom has more power. So I get x to the 5th on the bottom.
Fourth.
Oops, 4th. And now what about over here? I've got y to the 9th times y to the 1st. That's a total of,
Y to the 10.
okay. So we get y to the 10th over y to the negative 2. What's bigger, 10 or negative 2?
10.
So the y's are going to be top. Now what's my power going to be? I got to subtract. 10 minus negative 2 is 12. Good. There's my answer. Okay? See how that works? Would you agree that I probably didn't need to write that step out? I probably could have just done something like this. I probably could have just said, right, done that. And I could have, then I could have just, the variables are simple, aren't they? Because the variables, all I'm going to do with the variables is I'm just going to say x to the 1 divided by x to the 5th is x to the 4th on the bottom. Y to the 9 plus 1, so y to the 10 divided by y to the negative 2 is 10 minus negative 2, 12 on the top, right? I can do all that stuff just kind of scratching things out in my head and get to that answer in one step. But this is how we think about it, at least.
How can you times 3x and 3y when they're different variables?
Because the 3's don't care what they're being multiplied by. 3 is just a number, right? The 3 has no idea it's being multiplied by a y or an x. It's just a plain old 3. So when I multiply straight across, 3 times 3 is just 9.
Oh.
Okay? It's not attached to anything. It's just a coefficient. Okay? Questions on that? All right. Let's try one more like that, just because I think if we get through, if you get to the point where that's comfortable, that'll save you a lot of grief later on. And the reason I'm looking ahead for you guys, because I know that we're going to be doing some stuff soon where we're going to be dealing with in chapter 7 where we're doing the same kind of thing with fractional exponents. And it really pays to be very comfortable with what we just did before you move into chapter 7. So, let's try this guy. Okay, so numbers first. Do we see some cancellation and reduction that we can do here? William?
We can cancel the numbers.
Okay, good. We can, because, and the reason we can do this is because we're multiplying these fractions, right? So then I can do that. 7's cancel completely. What else? Okay, 12 over 4 reduces to
3.
Okay, so that becomes a 1, that becomes a 3. And so in my answer over here, the number part is just what? 3 on the top. Okay? And it's possible, if I end up with nothing on the bottom, I don't even need the fraction, do I? Right? But we might need it, so we'll put the fraction part in. Now what about the x's? Stare at that for a second and tell me what's the total power of x going to be and where's it going to be?
6.
Okay, so I get x to the 6th on the top, right? Because I get 1 plus 5. What's the bottom power of x?
X4.
Okay, so what do I end up with?
X2.
Yeah, okay. I end up with 2 left over on the top. Okay, what about the y's? On the top I get
2.
3.
3, on the bottom I get 1.
Y2.
Good. So I just get y squared, and that's my answer. I don't need fraction. Right? Okay?
Sorry.
Geometry.
Jess work today?
Jess. Bring up the
Really hope it's Jess.
Okay, so how about this guy? So now on these kinds of problems, they're going to give us the geometrical formula that applies. What we want to do here, this is a sphere, and we're going to try to write the volume of a sphere,
Can you just draw it? No.
which is 4/3 pi r cubed. Okay, but we want to write this in terms of x. In this case, we know that the radius of the sphere is x over 3, or 1/3 x. So what do I do?
Is that
Plug it
a
in.
4 or a 9?
That's a 4 on the top. 4/3 pi r cubed. So what am I going to do? If I want to write this formula in terms of x, I have to, quiet please, I have to make a substitution, right? So what substitution am I making? Yeah, x over 3 is going in there, right? Agreed? So then my volume is going to look like this. Volume is going to look like 4/3 times pi times x over 3 cubed. Okay, so what's the property of exponents that we use here? It's not a big deal.
What's that little thing that you circled the top?
R for radius. Yeah, that's our radius. But in this case, the radius is going to be x over 3. Okay. So what's the property of exponents that applies here? If I take a quantity, a fraction in this case, to a power, what do I do? Okay, now hang on. I'm taking this to the 3. I'm going to distribute that 3 to both parts. I'm going to distribute it to the factor on the top and the factor on the bottom, right?
Cubed over 27.
Okay, good. So then I'm going to get v equals 4/3 times pi times x cubed divided by 3 cubed, which is 27, right? Now the pi, so to finish this off, all I've got to do is just multiply all these fractions straight across. The pi is the same as pi over 1, right?
Yeah.
So when I multiply straight across, I'm going to get, my number is going to be 4 divided by 3 times 27 is 81. So I'm going to get 4 over 81, takes care of all the number parts, times pi, times x cubed.
So that weird sign is pi, kind of like a T across.
Yeah, that's a bad pi. Here, I'll make it better.
It's a circle with a couple slices in it. So I do my pi.
A what?
Circle with a couple slices.
Okay? Okay, so. All right. So then, what 6-1 amounts to, honestly, is just a lot of that. Just a lot of practice, doing problems where you have to do some exponent stuff. Yes, sir.
Make sure you don't lose a lot.
Because 3 times 27 is 81. Okay? So these guys. Okay, what I want to do today, I didn't really plan this, but it's just kind of the way the lab situation right before spring break, it's kind of, today's a horrible day. Third period's a bad period for labs. I do have the lab for sure tomorrow, and I'm 99.9% sure I'll have it on Friday. So you're not sure? I'm almost sure. So I couldn't get it today. I would have done this later in the week, but here's what I'll do. I don't want to try to do too much, but I want to just get you, I want to give you some concepts to think about. And I think you're going to want to, I'm not going to load you up with a ton of homework over spring break. I don't want to do that. But you are going to have assignments for 6-1 and 6-2. Okay? I think you can probably, if you want to, get those done even beforehand. Yeah.
Are those going to be due during spring break?
6-1 and 6-2?
Yeah.
No, I won't make them do until, like, the end. I mean, I don't expect you. And if I were in your shoes right now, what I would do is I would say, okay, I'm probably just going to crank those out this week so I don't even have to worry about it over spring break. Okay? 6-1, a lot of people have 6-1 done already. 6-1 does, once you get the hang of it, it doesn't take very long. Okay, so here we go. Take a look, please. I'd rather not have to keep you in here another day. I want to get this done today so we can be out of here for the rest of the week. Polynomial functions. What does it mean to be a polynomial? Now, this looks horrible, but this is the kind of thing I want you to get used to seeing in a math textbook. Let's make sense of this. So what is this saying here? We're saying we have some function f of x equals, I've got a sum of all these different terms, and that's what a polynomial is. A polynomial is a sum of terms. Actually, I'll tell you what, you already know what they are because you've already dealt with them. Last chapter, we dealt with quadratic polynomials. That's all they were. Quadratic functions are polynomials. So are linear equations. Those are also, or linear functions are also polynomials. We're just going to kind of move that trend forward a step or two in this chapter and look at some bigger versions. Quentin, please. Yes.
What are the subscripts?
Okay, the subscripts. So let's talk about that. What does this whole thing mean? Now, if I look at each of these terms, the first term has a subscript n on it. The second one has a subscript n minus 1 attached to it, and so on, all the way down to a subscript of 1, and then a subscript of 0. So what that's saying is that we're not going to pin ourselves down to a specific polynomial. This is going to represent any possible polynomial you could ever build. The n is just keeping track of how many terms are in this polynomial. This is the 0th term, that's the first term, second, third, fourth, all the way on up to the nth term. So the subscripts don't really, they're just keeping track of the number of terms we have. That's it. Okay? So it's really not that big a deal. What this is just doing is expressing a pattern. If we picked a polynomial where n was 2, for example, that's what we dealt with in chapter 5. That would mean that we would have, if n was 2, then we would have a sub 0 would be the last term. Then we'd have a sub 1 times x, and then the last term up here would be 2. We'd have a sub 2 times x squared. Now what that really would be is just ax squared plus bx plus c But instead of calling it B and C, we're calling it A sub 1 and A sub 0. Okay, don't worry about that. That is not a big deal. Here's the only thing I want you to know. So that's what this represents. But what a polynomial actually means is just a sum of terms with these two rules. Okay, and if you get this, you're fine. This is all you need to know about polynomials. Polynomials, each term in the polynomial is going to be a product of a number, a coefficient, and a power of x. The coefficient, right, the a part of those terms, can be any real number. There's no restriction. It just cannot have an I in it. That's the only thing it can't be is imaginary, but any real number would work. So for example, pi would be fine, or the square root of 17 would be fine, or any fraction, or any decimal would be fine, as well, of course, as any integer. Now, the powers of x, though, the exponents have to be integers and 0, so I guess whole numbers, right? Because really what this is here is x to the, I have x to the 1, and then there's an invisible x to the 0 there that we just don't write, because x to the 0 is equal to 1. Remember, anything to the 0 power is 1. Okay? So all of the exponents up here, even including this last term, they have to be either 0 or positive integers, so whole numbers. Those are the only two rules. Coefficients of each term, real numbers. The exponents are whole numbers. Okay? If that's the case, if I've got a sum of a bunch of terms that meet those criteria, it's a polynomial. So let's try, I want you to identify whether, determine if these are or are not polynomials. Get a little practice with this. Okay, so while we're on this slide, I guess, when we write out this polynomial then, we want to write the terms in descending order of power of x. So the biggest power of x goes first. That's the leading term. Then the next biggest power of x comes second, all the way down to what we call the constant, which won't even always have to be there. It could be 0, right? But so the last number that's by itself with no x attached to it, we call the constant term. The biggest power of x, which we could call n if we want to, is the degree of the polynomial, right? So a quadratic, let me write down an example of a quadratic function. What if I have something like this? F of x equals 3x squared minus 7x plus 11. That's a polynomial, right? Agreed? I've got a sum of 3 terms. Does it meet the criteria? Are the numbers in each of those 3 terms, not the exponents, but are the numbers, the coefficients, are they real numbers? Yeah, they are. Are the exponents all whole numbers? They are. No decimals, no negatives, nothing weird, right? So that is a polynomial. What's the constant in that polynomial? 11, right? There's the number that's times x to the 0. You don't even see the x, just by itself. What's the leading coefficient? That means in the leading term, the biggest power of x, what's the coefficient of x? 3. So 3 is the leading coefficient. What is the degree of the polynomial? 2, because that's the biggest power of x. You got it. That's how it works. Okay?
Movie time.
Okay. We want to write it in standard form. It's descending order. Okay, so here are the types that we've already dealt with. If it's degree 0, that's kind of a goofy one. That's just a constant. Okay, although technically that's a polynomial. Linear, right here. F of x equals some number times x plus some number. Now we've seen this, only we just call the coefficient something different. When we're dealing with it as a polynomial, we want to write them in order so that we can see that the power of x is matched by the coefficient, right? So whatever x to the 1 goes with, in the most general way of writing that, we call it a sub 1, to know that that's the coefficient of x to the 1. A sub 0 is the coefficient of x to the 0. Now we wrote this, back in the day, we wrote this as just mx plus b. Same thing. M is just a number, and so is b. They're constants, right? If we write it as a polynomial, instead of m, we'd write it as a sub 1. Instead of b, we'd write it as a sub 0. But it's the same thing. It's the same exact thing you've already done, okay? What if we take a second degree polynomial, which we just did? That's going to be quadratic, right? And because this is x squared, we'd write that coefficient as a sub 2, right? Because this is x to the 1, we'd write that as a sub 1, and then a sub 0 is the constant. And notice this is the way, isn't this the way, do the calculators do it this way when you do regression? I can't remember. Do they have A, B, and C? I think they do this, don't they?
They have ABC.
Oh, they do have ABC. Never mind. I couldn't remember. Okay, but this is just like what we called standard form, only we called it ax squared plus bx plus c before, right? Same thing, though. They're just numbers. A, B, and C are just numbers, just like those are, right? Okay. It's really not a big difference. It's just, if you treat it as a polynomial, this is how we would write it. Okay, then the next one would be cubic. Okay, and all we do is add another term out in front. So now the biggest term is x cubed, so we have to have this term out in front that's a sub 3 times x cubed. Can you kind of see why we don't use letters anymore?
Yes.
Because if we did, well, then we'd have to go from ax squared, bx plus c, then all of a sudden we'd have to have ax cubed plus bx squared plus cx plus d. It gets to be kind of confusing, doesn't it? This way we always know that a sub 2 goes with x squared. So it really is a better scheme, even though it's different. And then the last one that we'll name is a quartic. Fourth degree polynomial is what we call a quartic, and we just add one extra term out in front. That's it. So each time we get a bigger polynomial, we're just adding one extra term with a bigger power of x, and that's it.
We have a question.
Yeah.
So the linear one?
Yeah.
Up there, that's like a line, right?
Yeah, it's a line.
And then the other one's a u. So what's the other two?
Okay, so yeah, a linear equation is a line, a quadratic is a parabola. If you do a cubic, it's always gonna look kind of like this. Here's sort of it's gonna look like that, or it could look like that. But it's gonna have a couple different, and we'll talk more about this later. The big difference is the end behavior is gonna be opposite. On a quadratic, when we have a parabola, to the left and the right, either both of the tails go up, or if it opens down, they both go down. But on a cubic, one tail goes up and the other goes down. And it could be reversed, but there's always going to be opposite end behavior. And we'll talk more about that, not probably today, but we'll get to that eventually.
And then the other one just has another loop going back down.
And then, right, and then the other thing this has, that a cubic has, that we'll start to talk about, it's going to be a little while from now. But notice that this had, how many turning points does it have? A cubic could have, it might have one, but it could have up to 2. It could turn twice. So we're going to establish a relationship later that says the degree of the polynomial, if it's 3, then 1 less than that is the maximum number of turning points. So for a parabola, when it's x squared, the degree is 2. It can only have 1 turning point. And that's the vertex. But as we get bigger and bigger polynomials, they can turn more often. Okay? So what about a quartic? A quartic would look like this. Remember, that's n equals 4. So it could look, yeah, it would look something maybe more like that. Right? Now it could just kind of look like, depending, if I were to graph, that's kind of the generic one. That's sort of what it could have up to 3 turning points because it's a 4th degree polynomial. But if I just graph y equals plain old x to the 4th, it just kind of looks like a squashed out parabola. It just looks like that. So it could look like that too. Okay, we'll get into that more later. Good question. So you tell me, is that a polynomial? Does it meet all the requirements? Yeah, looks good. All the coefficients are real numbers. All the exponents are whole numbers. Is it written in standard form? No. What would I have to do? Yeah, I got to put the x to the 4th term first. Okay. So it is a polynomial. What is the degree? 4. Good. What's the leading coefficient? Say it again. Yeah, I think I heard people say it. It's actually -3, isn't it? Because that should be the leading term. The coefficient of the biggest power of x is the leading term. What's the constant? Good. You got it. Okay. So that's standard form. And that's what you told me. Okay? Okay, what about this guy? Something looks odd there. What's odd? Okay, that exponent. I can't have a variable in the exponent and have that be, that's not a polynomial, it's something different, right? That's an exponential function. So that one, we can see there's something that doesn't fit the mold. That's not a polynomial, okay? Because it has that exponent of the variable, okay? What about this guy? Any red flags there? Yes, there's one. Say it again. That's okay. There's coefficient of 1 there. Because the 1, we don't have to write it, but it's there. But there's something else wrong with
The
that.
negative coefficient.
The negative exponent. Exponents have to be whole numbers. They can't be negative, right? So that's a problem. The exponent is not a whole number. And then lastly, what about this guy? Yes. Yes. Looks weird, but checks out, doesn't it? Right? The numbers, the coefficients are all real numbers, no i's, and the exponents are all either positive integers or 0. So yeah, it is. It's not in standard form, but we could put it in standard form, right? Leading coefficient is pi. Constant is negative root 2, and the degree is 2. Good. Okay. All right, last thing I want to show you here is a shortcut. Okay, let's just see if we can.
I like the long way better.
Okay, now, evaluating polynomials. I want you to, it's real important that you know what the word evaluate is. And I think one of the things we do in math a lot of times is we throw these words out and people never get totally comfortable with what they mean. Evaluate is one that we've talked about before, but I'm going to hit it again. It's really important that you know what we mean by that. It doesn't mean solve. Evaluate means something easier. Who can tell me, what does it mean to evaluate something? So, for example, if I want to evaluate this polynomial when x equals 3, what am I doing?
Simplify.
No? I mean, in a manner of speaking, but not strictly. What do I do when what does value mean in math?
You're evaluating value of something.
Yeah, good. And value in math means number. Okay? The value of something has to do with its numerical value. So when I'm evaluating, that means I'm plugging numbers into the function and getting back the number value of the function. So in this case, all I'm doing is taking that 3 and plugging it in for all of the x's and then finding out what I get, right? Okay, no big deal. Now I want to show you something on a calculator. There's an easy way to do this. It's not a hard process. Obviously, you don't need a calculator for that, but if you have one, it's pretty handy. Okay, so let's put in. Here's how you can do this real quickly. Like if I want to repeatedly evaluate polynomials, which you're going to be doing, here's a good way to do it. Let's put in the polynomial. So I'll just type in this case, 2x to the 4th. 2x to the 4th minus 8x squared, right? Plus 5x minus 7. Okay, plus 5x minus 7. Okay. Now, if I want to put values in for x, there's a great trick. All I have to do, if I hit enter, it gives me back some random number. Why is it doing that? Because what it's doing is it's taking whatever value happened to be stored in x in the calculator and it's plugging that in. Now, I don't know what that value is. I'm going to choose the value, though. I want the value that I plug in for x to be what? 3. So what I do is I type in a 3, and then right down here it says STO on your calculator. What do you think that stands for?
Storage.
Store. I'm going to store that number 3 as x. So in other words, I'm going to give the value 3 to the variable x. And if I hit enter, it's just going to say 3. Okay? Because now it's in there. But now I want to know what's the value of this expression that I created up here when I've got a value of 3 in for x. So all I have to do is just go back up and, whoops, grab that expression and hit enter, and it'll pull it back down. And now if I hit enter, there's my answer. Okay, what it did then is it took this and it said, okay, x is 3. Now if I evaluate this, I get 98. Yes, ma'am?
On the 83, how do you go up and grab that?
Okay, good question. On the 83, instead of going up, you have to just hit second enter, and it'll roll it back up one at a time. But you can still do the same thing. Okay? There's another way you can do this also. If I'm going to be evaluating a function for a ton of integer values, there's even a better way. This is the way most of the time you'll do it, because you're probably not going to be doing a whole bunch of different values. But if I were, I can just go to y equals, and I can put in, maybe you know what I'm going to do here. If I go up here and I clear out this first y equals y1, I'm going to store this as y1. So I'll just go 2x to the 4th minus, that's enough, minus 8x squared plus 5x minus 7. Okay? Just hit enter. And now if I go to table, if I go second table, now my table's not set up very well. My x's are going by really small increments because we were doing something in calculus. But so I'd want to go set the table differently. So I go second table set, and I want my start value to be, let's just say, how about 0? And delta table, that means, what are my increments of x going to be? I want to just go in increments of 1. So I'll just go delta table is 1. And now if I go back to second table, look what it does. For all these x values, it's giving me back the y values for that function. Okay? And then, of course, the other option is I could just graph it, right? I could also just graph it and go second calc value and choose an x value. But to me, that's a lot harder because then you have to get the thing on the screen. So in a way, this is easier to do, right? Make sense?
Yeah, that's awesome.
Okay.
Mark it.
That's a good place to stop. All right.
Indiana
Good job.
Indiana
32.